Creating operating systems is fun, but when something goes wrong, debugging can often be a big challenge. Many debugging features you are used to on your host machine are not available in your own operating system until you implement them. One of the easiest and most reliable ways of debugging is by printing text to the screen. However, using the actual screen of a virtual machine or a machine that you're testing on has many disadvantages. You can't use copy and paste, you can't search. If you write too much text, the scrollback will make most of it disappear. And what if you work on graphics? Now you won't see any debugging information and you have to guess what your operating system is doing. What if I told you there is a better way? Using serial ports for writing logs and reading commands is a pretty commonly used technique for debugging operating systems and software in embedded devices. Linux does this as well. Virtualization software can redirect serial output to a terminal or a file, which is very convenient. On real hardware, depending on the ports available on your development and test machines, you can use USB serial adapters or just normal serial cables. However, this requires creating a serial driver in your own operating system. While that's not the hardest thing to do, today we will look at an even simpler technique which works in Box and QEMU, the E9 port hack. The main disadvantage is that this method doesn't work in other virtualization software and also doesn't work in real hardware. But the big advantage is that it doesn't require any kind of setup or any drivers. In fact, all that we need to do is write characters to port E9. First, we need to enable this feature. In QEMU, all you have to do is add the debug-con stdio arguments to the command line. You can also write these logs to a file using debug-con and then file, colon, and the path to the file. In Box, we need to add this line with port E9 hack enabled to the configuration file. Something to note here is that Box writes a lot of informative logs, so if you want to get a cleaner output, it might be a good idea to either set the info logs of Box to ignore or redirect the logs to a different file. Once we do this, we can send characters by writing them to port E9 using the outbe instruction. To print a string, we just need to call this instruction multiple times for each of the characters in the string. A very cool thing is that we can take advantage of the host system's terminal processing features. For example, we can change the color of our text by using the ANSI escape sequences. Piping also works, so you can write the text to a file using the redirect operators or use utilities like grep to filter logs. If you are already working on your own operating system, you will most likely already have a way to print text to the screen. Let's explore a few ways in which we can integrate this functionality in our own operating system, starting from the simplest to the most complex. The simplest solution would be to modify your putc function so that it writes to both the screen and the host terminal. This way you don't have to change anything else. All the printf calls will be also sent to the host via the E9 port. Of course, this is not the best long-term solution, because the screen should be used to display the user interface, not system logs. The simplest way in which we can achieve that is to use the preprocessor to toggle between printing to the screen and printing to the host. Just define a macro somewhere, you can find it easily, and then use the preprocessor if directive to control which code should be compiled. Using the preprocessor is not ideal. Instead of selectively choosing where to print stuff, we just completely disable printing to the screen. How about separating the two functionalities and having separate functions for printing text to the screen, which will be visible by the user, and printing debug logs, which are just for us, the developers. The simplest way to implement this would be to create two sets of printing functions, one for the screen and one for debugging, but this will result in a lot of duplicated code, which is not ideal. One solution could be to have internal versions of the text formatting functions like putc and printf, which take a pointer to a putchar function as a parameter. Then we can use some pre-processing magic to create debug and printf that just call the same implementation but with different putchar implementations. The virtual file system is a component of the hardware abstraction layer, and it represents an abstraction for accessing files and folders. When you're building an application and want to read a file, you don't need to know what file system that file resides on, or whether you're reading it from a local disk or a USB drive or somewhere in the cloud. All you have to do is just provide a path. The virtual file system is the component of the operating system, which is where that path is parsed and linked to the actual file system and storage device on which the file resides. You are probably familiar with the fputc and fprintf functions from the C standard library. Let's see how we can implement these into our operating system. For this idea, we only need a very small subset of the functionality that's normally in the VFS.
In fact, all that we need is a VFS write function. I will make a dedicated video about building the VFS subsystem, but today we will keep things simple. We will start by defining a file descriptor ID, which is basically an integer that we will use to identify which file to write to. In the full VFS implementation, this ID will point to an entry in a table of opened files, but today we will just hardcode it. Next, we will create some constants for the standard I/O. The Unix convention is that file descriptor 0 corresponds to the standard input, 1 to the standard output, and 2 to the standard error output. Of course, this is your operating system, so you can use any IDs that you want. I just used the ones from the Unix convention, and in addition to these three, I also added the file descriptor ID 3, which corresponds to the debug port. The VFS write function will return the number of bytes written, and it will have three arguments: the file descriptor ID, a pointer to a byte array which will contain the data to write, and a size argument which contains the size of the array. Before implementing this method, let's go to stdio.c and refactor things. First, let's move out all the parts that deal with hardware. all the functions which interact with the memory address B8000 will be moved to a VGA text.c file in the i686 directory. This method only works on the x86 platform when we are in a VGA compatible text mode, so it belongs to wherever we put our drivers. I also renamed all the functions to start with VGA_ so that they don't conflict with anything else from stdio.c. We should also add the most important functions to the header file VGA text.h, more exactly the clear screen and the putc functions. This would also be a good time to implement the e9 putc functions, so let's create an e9.h and e9.c. I did a bit of an oopsie here. I used port E5 instead of E9. This was a mistake that I will discover later. The port is E9, not E5. Going back to stdio.h, let's start by creating the file variants of all the functions. Something I dislike about the C standard library is that fputc and fputs have the file passed as the last parameter, while for printf it is the first parameter. While we could change that, I think it's best to be predictable. We want to implement multiple versions of printf, so we have to put the main implementation in a vfprintf function, which is just like fprintf, except that the arguments are passed through a VA list instead of the variadic arguments. We will see in just a moment how that works. Let's start by implementing the first function, which is fputc. All we need to do here is call vfsWrite with the character that we want to write. For putc, we can reuse the old implementation, but instead of calling putc, we will call fputc. Next, we have vfprintf, where we can just copy the old implementation. The main difference is that we don't need to copy the VA start and VA end. The VA list is passed as a parameter. Again, we have to replace all the calls to putc and puts with fputc and fputs. And of course, we also need to change the number printing functions. For fprintf, all we need to do is initialize the VA list, call vfprintf, and then call VA end. I also have this fprintf buffer function, which is used to print memory in hexadecimal. Again, we replace putc and puts with fputc and fputs. Next, we have the standard output versions of these functions. All we have to do here is just call the file variants, but using the stdout file that we defined earlier. In the printf implementation, we have to initialize the VA list and call vfprintf, just like we did with fprintf. Now for our pièce de résistance, we will also create debug versions of all of these functions: debug C, debug S, debug F, and debug buffer. The implementation is almost identical to the standard output functions, except that this time we are using the debug file instead of stdout. Finally, we can implement VFS write. As I mentioned before, this is not the final implementation of the VFS. Our focus today is on the text printing functionality, not on the file management system. The simplest way to implement this is to use a switch. If the file is stdin, write doesn't make any sense, so we will just return 0. For stdout and stderror, we call the vga putc function for each of the characters in the array. If you want, you can make the standard error text more visible by changing the color. Finally, for the debug file, we call the e9 putc. We're almost done, all that's left to do is test that everything works. And fix all the compilation errors.
This was a mistake that I will discover later. The port is E9,
not E5.
Yay!
When your operating system will become more advanced, you will end up having to go through a lot of logs. Finding problems will become tedious, like searching for a needle through a haystack. Luckily, there are many ways in which we can improve our logging to be even more easily read and even more useful.
One of the most useful improvements is to add log levels, like info, warning, and error. Since the host terminal will interpret the ANSI escape sequences, we can use different colors for the different log levels, which will make differentiating them much easier. And of course, we can also filter logs based on severity. Another improvement would be to add another parameter for the module. This will allow us to filter for logs that are coming from a certain component. For example, we can filter to only see the logs coming from the memory manager. For this implementation, I used macros to define log functions for all the different log levels, all of which call the logf function. In the logf function, we start by setting up the VA list from the variadic arguments. Next, we will set the text color depending on the log level. What I'm doing here is just using fprintf to print to that debug file an ANSI sequence that will change the color. For the colors, I used this weirdly defined array. In C, you can use this syntax to link the enum entries to the array values. After setting the color, I printed the module name, and then using vfprintf I printed the message. Finally, I printed a new line character and reset the color to the default. Let's see this in action. Very cool stuff.
As your operating system grows, you may find additional things that will increase the usefulness of logs, like what CPU they're coming from or what process, what thread. There's a lot of freedom in how you can design your logging system. It might make sense to stop looking at text and write logs using JSON or XML, which will allow you to use more advanced software for reading and sifting through them. Logging is one of the most useful tools in our arsenal, and today we learned how to build better logging into our operating system. I hope you found this information useful to help you move forward with your OS and make debugging a little bit easier. At some point I will also make a video about creating the serial driver, but there are still a couple of really important topics to cover. If you need any help or you would like to join our community on Discord, there's a link in the description below. Until the next time, have a lot of fun and bye bye!